Hi everyone, I'm Chen Zhao, a PhD student at University of Chinese Academy of Science. In this talk, I will briefly introduce a Julia package for the ZXCalculus, ZXCalculus.jl. So what is the ZXCalculus? It is a graphical language for quantum information. For example, we can use the ZXCalculus for simplifying quantum circuits. In the ZXCalculus, we will do graphical calculus on ZX diagrams. If you are familiar with tensor networks, you can regard ZX diagrams as a special type of tensor networks, which are generated by two types of tensors, the Z-spider and the X-spider. With the Dirac notation, we can express these spiders explicitly. If two spiders are connected, it means that the corresponding indices are contracted by tensor contraction. In principle, we can represent any quantum state and quantum gates as ZX diagrams. For example, the zero state and the plus state, and the single qubit gate rotation Z, rotation X, and Hadamard gate by Euler decomposition. Also, two-qubit gate C0CZ, which can create entanglement in quantum computing. To do graphical calculus, there are rewriting rules in the ZX calculus. Each rule will rewrite the ZX diagram to another equivalent one. The ZX calculus gives us a powerful tool to reason about quantum information. There are a lot of applications of the ZX calculus, including quantum circuit simplification, quantum codes, quantum machine learning, and quantum NLP, and so on. After introducing the ZX calculus, let's take a look on this package. The low-level data structure to represent ZX diagrams is the multigraph data structure. We developed a package, multigraphs.jl, for this. And based on multigraph.jl, we define ZX diagram and ZX graph. We provide various methods to create ZX diagrams. Moreover, you can convert quantum circuits, which are defined in Zhao, an efficient and extensive quantum simulator in Julia, to ZX diagram. And you can use the ZhaoPlots.jl package to visualize ZX diagrams in ZXCalculus.jl. We provide APIs for matching and applying rules. Based on these rewriting rules, we developed some state-of-the-art circuit simplification algorithms. Multigraphs.jl is an efficient library for the multigraph data structure. It is based on the LightGraphs API, and it is open sourced on GitHub. Here are some examples that show how to use this package. The multigraphs should be used together with the LightGraphs. This line will create a multigraph with two vertices but no edges, as shown in this graph on the right. We can use the addEdge function to add multiple edges to multigraphs. Here we add a multi-edge of multiplicity 3 between vertex 1 and 2. And addVertex function will add a new vertex to this multigraph. Here the new vertex is labeled 3. If multiplicity is not given, it will be regarded as a simple edge. RemEdge function will remove multiple edge from the multigraph. Here we removed a simple edge between 1 and 2. And also we can iterate all multi-edges in the multigraph. Based on multigraphs.jl, we define ZX diagram and ZX graph, and we provide various methods to create them. For example, you can create a ZX diagram from a multigraph directly, but the more efficient way is to create a ZX diagrams from quantum circuits. Here we give some examples how to create a ZX diagram as a quantum circuit. Firstly, using ZX calculus. This will create a ZX diagram of a 3-qubit empty circuit, as shown on the right. Using pushGate function, we can add quantum gates at the end of the quantum circuit. Here we added Hadamard gate, C0 gate, and CZ gate into the quantum circuit. Now you can use the visualization tool Yao plots to draw the ZX diagram that we create. Moreover, we can use the Yao ZX package to do conversion between QBIR, the quantum block intermediate representation, and the ZX diagram. For example, we first create a quantum circuit with 4 CNOT gates in the Yao blocks. Then, using Yao ZX, we can convert it to a ZX diagram. Here is the ZX diagram we get. To use rules in the ZX calculus, we can use the match and rewrite function. In this example, we will show how to get the simple identity 2 Hadamard gates equals to an identity. We first create a ZX diagram with 2 Hadamard gates by using pushGate function. On the right, we first match the I2 rule, then apply this rule on all matched subgraphs. Finally, we get the identity. By now, we have shown how to use this package for creating, manipulating, and visualizing ZX diagrams, so that you can use this package for researching. Moreover, we implement these 3 circuit simplification algorithms in these 3 papers, so that you can use it as a circuit simplification engine. We also use it as an optimization path in a quantum compiler project that we are currently working on. This package is much more faster than the previous Python implementation. Here are benchmarks for the phase teleportation algorithm. We run this algorithm on different circuits with different sizes. For each circuit, the runtime of ZX calculus is scaled to 1. And you can see we have 6 to 50 times speedups comparing to physics. And for bigger circuits, we will have more speedups from our experiments. In conclusion, ZX calculus is an efficient Julia library for the ZX calculus for researching, and it provides a state-of-the-art circuit simplification engine. This project is a JuliaCon2021 project, and all codes are available on GitHub. Thanks for my mentors Roger Luo and Jingguo Liu for their help. That's all for the talk. Thank you.